All right, welcome to worksheet number 6, the derivative as a function. This corresponds to section 2.2 of our textbook. In this section, we'll look at the derivative as a function, find the derivatives of more functions, so we'll kind of deal with the different functions, and how it affects the graph. Also, we'll investigate the second derivative, which is the derivative of a derivative. All right, so kind of review f of as a function. Then we can set the we can define the derivative of function defined by f prime, c little dot, f prime of x. So limit of x, f of x plus h minus f of x over h. So previous section, we look at a particular number a. Here we're looking at a general point x. That's why it's a derivative as a function. So x can be any number, provided the limit exists. So nothing is really different. Instead of using a, here we're using x. That's pretty much it. We have a different notation for the derivative. So the one that we're going to use most often is f prime, that little dot, f prime of x. Another notation we're going to be using is df over dx. So this is saying, hey, there's a function f, df dx means take the derivative of f with respect to x as a variable, right? So this kind of means that. Another way you can say that is y prime. This is so assuming y is equal to f of x, right? So again, sometimes we'll use x and y, especially in the graph. So if that's the case, then instead of saying f prime of x, I'll say y prime, right? And then I can also say, because it's y prime, if I were to kind of use this notation, I can say be dy over dx. It's kind of similar concept. I'm taking y and to take the derivative with respect to x. And another way to say it is d dx and then f of x. Basically, I can kind of separate d dx. This means take the derivative of what? F of x, right? So these are just different notations we're going to be using. All right, let's look at example 1. Find the derivative of this function, x squared minus 3x plus 2, using the definition. Okay, so here's your definition. I'm going to kind of do the setup and see if I can have you finish it. So limit, first of all, h goes to 0, x plus h minus f of x over h, where my f of x is this thing. So first I'm going to have to kind of write out f of x plus h. So what that means is instead of plugging in x here, I'm going to plug in x plus h. So how does that work? Limit h goes to 0. So that's x plus h squared minus 3x plus h plus 2. So that's the first part. X plus h squared, 3x plus h, and then 2. And the second part is minus f of x. Okay, so minus x squared minus 3x plus 2 all over h. Here, I guess I just keep going here, limit. So let's see, x plus h squared, so that's x squared plus 2xh plus h squared. And then second part is minus this, so negative 3 get this distributed. So minus 3x minus 3h, and then plus 2 minus x squared minus 3x plus 2 over h. Let's see if there's any cancellation. There is x squared here, there's x squared here, they're going to cancel out. And then negative 3x will also cancel out, and then plus 2 will also cancel out. Okay, so what's left? So limit as h goes to 0. Here, I forgot to write that here. 2xh plus h squared minus 3h over h. Okay, so I can do on the top, every term has h in it. This one is h squared, so basically that's 8 times h. So let me just factor that out. H, 2x plus h minus 3 over h. Okay, so I factored out h from every term because every term had h in it. So then I can cancel that out because there's h on the bottom. Okay, so this means I get h goes to 0, 2x plus h minus 3. Now I can let h goes to 0, so then this goes to 0. So all I have left is 2x plus 3. Okay, so as a function, if I take the derivative of this at any point, I get this. So if I take the derivative of this at when x is equal to 1, then basically the derivative is going to be 2 times 1 plus 3. If I take the derivative of this at x is equal to 5, for example, then, well, that'll be 2 times 5 plus 3 will be the derivative there. So this kind of tells you it doesn't matter where you take the derivative, I just have to plug it in once I get the derivative. Okay, so I can say this is equal to f of x. All right. All right, next to example 2 and example 3, a little bit more involved. I'm going to get started, and then I'm going to have you finish it. So kind of do the same thing. Example 2, it says find the derivative of this. Okay, fine. So we'll do the setup. So limit as h goes to 0, g of x plus h minus g of x over h. So h goes to 0. G of x plus h, again, how do I calculate that? Instead of plugging in x here, I'm going to plug in x plus h. All right, so let's see. It's 3 over x plus h minus 3 over x. And the second portion is just g of x, so I'll just copy that. And then all over h. All right, so I have fraction minus fraction over fraction. Okay, there's a lot of fraction. So I think the easiest way to simplify this is if I look at the top, I can just simplify the top first. X plus h is the denominator, x is the denominator, so I want to have a common denominator. They don't really have any common vectors, so I'll just multiply x plus h on the right, and then x on the left expression. So having said that, that'd be limit as h goes to 0, 3x over x plus h times x minus 3x plus h over x plus h. So why do I need to do all that? Because now on the top they have a common denominator, so I can now subtract them. Because in order to add or subtract, I have to have a common denominator for fractions, right? So now I do x plus h times x. So on the top, I have 3x minus 3 parentheses x plus h. So top, I can write 3x minus 3x minus 3h. So how do I get that? I distributed negative 3x here and then negative 3x there. So that's what I got. All over h. I'm gonna, so I'll, okay, I have that cancellation. So I got a little bit simpler. Now I'm going to have you finish the rest of it and see what answer you get. All right, so once you work everything out, you should be able to get negative 3 over x squared, dot, dot, dot. Okay, and then same for example 3. This is the one with the square root. I'll do the setup, and then I'm going to have you finish the rest of it. How do I get started? Kind of same thing. Limit h goes to 0, f of x plus h minus f of x over h. So limit h goes to 0. So I'll plug in x plus h here. So it can be kind of tricky. 2x plus h minus 5 negative 2x minus 5 over h. So it's a little bit complicated. Again, the first part, instead of plugging in x, I plug in x plus h. So instead of 2x minus 5, I got 2x plus h minus 5. And the second part is just f of x. So that's that. We've seen this type of expression before. I have radical something minus radical something. So my hint is maybe multiply conjugate. Multiply conjugate to simplify. Because as of now, if you plug in 0 for h, I have 0 on the bottom. Radical 2, if h is 0, radical 2x minus 5, radical 2x minus 5, so top is 0, so you get 0 over 0 case, which means you got to do more stuff, which means here, actually I can do conjugate, multiply conjugate to simplify this. So I'll have you pause and finish the rest of the example 3. And if you did it correctly, it should be get 1 over radical 2x minus 5. All right, let's look at the next question. It gives you example 4. Gives you the function, kind of looks crazy. Fortunately, they calculated f prime, the derivative, for us already. They graphed the original function, which is f, the blue one, and then graphed the f prime function. Right. This is x squared or something, so it's just a parabola. This is x cubed, so it looks like this. So let's look at f prime of 1, the first question. Well, f prime, so I'm looking at here. Generally, it's this. At particular 1, all I have to do is just plug in 1 here. So plug in 1, negative 2 times 1 plus 10 plus 8, so that's 0. Okay. And we can kind of do the same thing, f prime of 2. I know the general formula for f prime, the derivative. It says at 2, that means I just have to plug in here 2. Negative 2 times 2 is negative 2 times 4, so negative 8 plus 20 minus 8 over 3. So they'll give you 4 over 3, and so on and so forth. So when I plug in 4 for the next question, plug in 4 here, as a result, you're going to get 0, and then you're going to get 4 over 3 again. You're going to get negative 8 over 3, and then you're going to get negative 8 over 3 as well. So I'm just plugging in a bunch of different points, get the answer. Notice that some answers are 0, some answers are positive, some answers are negative. Here, I want to kind of connect the graph with these answers. So one of the interpretation of the derivative was f prime x represents the slope. It represents the slope of the tangent line. So I want to see how that matches up. So tangent line of f of x, right? So f prime of 1. So the original graph is blue one. Tangent line is like the line that touches graph once. Right? So at 1, tangent line is just the horizontal line. Like this graph meets this line right here. So tangent line at x is equal to 1 is basically horizontal line, which has 0 slope. That's why it's this. That's why the graph of the red one is 0. It's kind of confusing. The next one, f prime of 2. So again, this is my f2 is right here. So if I were to draw a tangent line, it's going to go like this. So I don't know exactly what number. Again, tangent line is the derivative represents the slope of the tangent line. So this is the tangent line. I don't know what the slope is exactly, but I know it's going to be positive because it looks like this, right? So any line that goes this diagonal will have a positive slope. So I knew it was going to be positive. I didn't know it was going to be 4 over 3. But by just looking at the graph, I knew it was going to be positive. Here, f prime at 4, 1, 2, 3, 4, right here. Again, my graph, the original graph has horizontal tangent line. That's why it was 0 slope. And then if you look at like f prime of, let's say, 5. Where's 5? 5 is here. If you look at my original graph, the blue graph tangent line looks like this, which is like basically slope, negative slope. It's going like this. So again, any line has diagonal like this way, then your slope is going to be negative. So again, I knew the answer was going to be negative. I didn't know it was going to be 8 over 3, but I kind of knew the answer was negative. So it kind of matches up. So here, what do you notice about f of x when f prime of x is equal to 0? That's when you have this horizontal tangent line. So I'm going to say here, horizontal tangent. And then what do you notice about f of x when f of x is positive? Again, that means your tangent line has a positive slope. So that means tangent line looks like this slope, right? And when it's like the other way around, your tangent line looks like this. It's going down, right? Because if you have something like this, it has a positive slope. If you have something like this, it's a negative slope. So by looking at the graph, I could kind of tell what kind of derivative you're going to get by looking at the shape of the graph. All right, let's look at the next example. Ooh, here, okay, we have a different graph now. of f of x is, different function, f of x is absolute value of x, I can think of that as absolute value of x is negative x if x is negative, positive x if x is bigger than or equal to 0. Because absolute value is always positive, so if you're starting with a negative number, you just put the negative in front of it to get the positive answer. If you were looking at the graph looks like this, right? It's just a V-shaped graph. So how do I find f prime of x? Again, if I look at graphically, slope of the tangent line, like here, if you look at any point on this side, tangent line is the line itself, which is -1 slope, right? So -1 if x is negative. If I look at the other side of the graph, again, tangent line is the line itself. It has a slope 1. So 1 if x is positive. So, okay, how about when x is exactly 1? Well, if I look at kind of like left limit, basically it's -1. If I'm looking at it as a right limit, it's +1. So left limit is not equal to right limit, so it doesn't exist at 0. So does not exist if x is equal to 0. So if you have a V-shaped graph, at this point, the tangent line doesn't exist. We don't know what the tangent line is. So is there a place where this doesn't exist? In this example, yes, right here. So generally speaking, the derivative doesn't exist when graph has this little sharp edge. Sharp edge. Like for example, the previous question, graph, the derivative exists everywhere because when you turned, it was more like a smooth curve. So we had a horizontal tangent line. For this question, when my graph turns, it turns like very sharply. It's not a curve, it's more like a straight line, there's an edge. So I'm going to call this like a sharp edge. So when we have a sharp edge, graph, the derivative doesn't exist. There are other cases when the graph has a hold or graph has a jump. And I'll explain that in more detail. So let's look at the next definition. F prime of a doesn't exist, then it's differentiable at a. So if the derivative exists, we'll say the function is differentiable at that point. And if it's differentiable on some interval, that means derivative exists every number in the interval. All right, so as we said before, absolute value is not differentiable at x is equal to 0. That means it's differentiable everywhere else. So I can say -infinity to 0 union with 0 to infinity. Right? All right. And next topic is the second derivative. So here, the derivative of the derivative. So you take the derivative first, and then can you take the derivative of that function again? The answer is yes. So it's called the second derivative. Let me highlight second here. Okay, so versus the regular derivative. Sometimes regular derivative is called the first derivative. So if you look at the notation here, you notice there are 2 dots or 2 dash thing. So this is the second derivative. And I'm going to read it as double prime, right? So second derivative, when I write it like f dot dot, that's double prime. Also, I can say it's y double prime df dx, except d square x and then dx square, indicating it's double second derivative. Same for d square dx square y, like this, right? So I'll probably use this notation and this notation the most often, double prime, okay? So it means take the derivative and then take the derivative again. So for example, example 7, f is x squared minus 3x plus 2. F prime is 2x minus 3, fine. F double prime, okay, so that means take this one, the prime, and take the derivative of that one more time. So f double prime is, so I'm going to call this g of x. So basically, f double prime is limit h goes to 0. So again, I'm not taking the derivative of the original function. I'm now taking the derivative of the derivative. So g of x plus h minus g of x over h. So that's going to be limit h goes to 0. I'm plugging in x plus h here. So that's 2x plus h minus 3 minus 2x minus 3 over h. All right, so I'm going to just multiply it all out. 2x plus 2h minus 3 minus 2x plus 3. Right, so that's going to be the limit. H goes to 0. 2x plus 2h minus 3 minus 2x plus 3 over h. A lot of cases, if you did it correctly, you're going to see a lot of cancellation here. So then what do I get? I get limit as x goes to 0, 2h over h. Oh, okay, h cancel out. So there's 2, just 2. Okay, so the second derivative is just 2. All right, so in terms of calculation, it's not bad. It's just the concept of the second derivative is there. In terms of velocity, the motion, so the regular derivative, first derivative, is instantaneous rate of change or velocity. So what's the meaning of the second derivative? Is the rate of change of the rate of change. It's also known as acceleration. I'll highlight this, acceleration. So velocity and then position. So the regular function, the original function is position, and then if you take the derivative, you get the velocity. If you take the second derivative, that means you take the derivative of the derivative, you get the acceleration. So like when you are in a car, you're going 60 miles an hour, do you feel it? Or if this car is going pretty quietly, you can't really feel you're going, right? So that means your velocity is 60 miles an hour, but you don't really feel anything. But when do you feel car moving? Like when you stops or when you starts, because your speed is changing. So again, it's the rate of change of speed. So that's what you feel is acceleration. So like this is what you feel in a car. This is what you feel, in a car. So when car stops or car starts, like start going up, then that's the force you feel is acceleration. Okay. So if s is the position, s prime is the velocity. So I'm just kind of saying the same thing. And then if you take the velocity, second derivative, which is the velocity, and take the derivative of the velocity is the acceleration. Acceleration. All right, and then can you take the derivative one more time? Yes. So that's the third derivative, triple prime, and then the fourth derivative, and then fifth derivative, and so on and so forth. So you keep if you have a function, you can keep taking derivatives. You get just the next derivative. Okay. I'm going to have you do example number 8. It just asks you to find the next derivative, second derivative, and the third derivative. All right. Next theorem kind of connects the differentiability and the continuity. So basically, if function is differentiable, then it has to be continuous, which is kind of nice. So we learned about some places where we have a limit, place where things are continuous. Now we're looking at the place where it's differentiable. So if something is differentiable, that means it's automatically continuous. That means it automatically has a limit. If it's differentiable, then we automatically know it is continuous. Converse is not true. Some functions are continuous, but it's not differentiable. Okay. So give an example graph where it's not differentiable. So we had first already know the absolute value. So not differentiable, right? So that's like sharp edge. Sharpable. When we have a gap, so even if you have like a smooth curvy function, but if it's missing a point, then not differentiable. And then, I mean, it's not continuous either, right? So that's the side note. Not continuous. And also, so this is the sharp edge. This is a hole. And when you have a jump, it also, so something like this maybe. Not differentiable. Also, it's not continuous. Also, limit doesn't exist, right? Limit does not exist. Whereas the previous, let me kind of go back to the previous one. Previous one, limit existed, right? So limit here, limit exists. So it's possible that limit exists here, but it's not continuous and it's not differentiable. Here it's continuous, but not differentiable. And the third case was it's not continuous nor differentiable, nor does it have a limit, right? Okay, so they are kind of related in certain ways. So let me try to organize those three. How do we connect limit, continuity, and derivative, differentiability, right? So for the jump, there's something like this, and then something like this, right? Limit exists, nope. Is it continuous? Nope. Is it differentiable? Nope. So if graph is substantially broken down like this, there is jump, then limit doesn't exist at this point. It's not continuous at this point. It doesn't have the derivative at this point, right? So this is like the worst or the most severe case. Sometimes your graph has a hole like this. I can find the limit. Limit exists, yes. But it's not continuous, so that's no. And then differentiable is not differentiable, right? There are cases where it has a sharp edge. Sharp. Limit exists at this point, yeah. Is it continuous? Yeah, I can draw it in one shot. Is it differentiable? No, because it's not smooth. It has a little sharp edge, right? So if you have it like this, it's called smooth. There's no sharp edge, there's no jump, no hole. So it kind of tells you how nice your graph is. Like this is the nicest graph. This is like not the nicest graph. Not that it's like one is better than other, but in terms of like a form. So the limit exists. For the last one, limit exists, yes. Continuous, yes. Differentiable, yes. So these are just different types of graph you're gonna notice, and then it depends on how it's given. We can have those three things in different format. All right, this worksheet was a little bit long, but we're pretty much done.